स्क्रीन दिसते का बघा.
नाही अजून सर.
आता
हा आता दिसायला लागले.
ओके. स्क्रीन दिसते धवल.
हो सर दिसते सर.
Okay, today we will see the operations of state diagrams. Previous lecture we have studied what is a state, what is event, what is a state transition, then state transition diagrams we have studied. Then what are the operations on state diagram? So the state diagram presented so far describe the patterns, events, states for a single object class. So there is only one operation is a controlling operation which is divided into four parts. So controlling operation in these state diagrams would be of little use if they just describe pattern of events. A behavioral description of object must specify what the object does in response to events. Operations attached to state or transitions performed in response to the corresponding state or events. So in controlling operation there is must be activity and the action. So an activity is an operation that takes time to complete. An activity is associated with the state. Activities include continuous operations such as displaying pictures on television, as well as sequential operations that terminate by one after another in the time interval, such as closing a wall or performing a computation. You are seeing watching movie or seeing serials on TV. This is the activity which perform some state one after another. That is the action or activity. So in this same way in object oriented modeling and design, so a sequential operation that terminate one after another with a specific time interval. So a state may control a continuous activity such as ringing a telephone bell that persists until the event terminate it by causing transition from the state. So initially in case of telephone, initially it is in ideal state. So when the action of ringing done, it will terminate after some specific time, and during that time its activity is the ringing. This is known as the activity of controlling operations. Then action. So controlling operation have a notation do a notation with a state box indicates the activity. A starts on entry to the state and stops on exit. Start on entry and stops on exit. A state may also control a sequential activity such as robot moving a part, so which progress until the completes or until the interrupted by event that terminates its prematurely. The same notation do A indicates the sequential activity. A begins an entry to state and stops a complete. In case of clock, there is second hand, minute hand, and hour hand. So whenever a power is on, that is a cell is on, the all the three hands runs. So the second hand runs for a 60 second, then and then minute hand runs for a 1 minute. This is a state. So whenever second hands entry starts at the same time minute hands entry start. So, and whenever second hand stops at the same time minute hand the stops. So there is a controlling operation in the state diagram. Another operation in the controlling, another part in the controlling, if an event causes a transition from the state before the activity it completes. If an event causes a transition from the state before the activity it completes, then activity is terminated prematurely. Suppose you have given a 3 hours a question paper for 100 marks and time starts at 2 o'clock and terminates at 5 o'clock. Okay, this is a time duration for 100 marks question paper 2 to 5. But sometimes you now in online examination, sometimes suppose you have started at 1:30, so half an hour the time before 2 o'clock, then your time termination at 4:30. So same case here, if an event causes a transition from the state before the activity complete, then activity terminated prematurely. For example, a robot might encounter resistance cause, causing it cheese moving. These changes are not really different. A continuous activity may be viewed as a sequential activity, that lasts the indefinitely. So last in previous slide we have seen the what is the activity. In this slide we will see what is the action. So an action is instantaneous operation. An action is associated with event. An action represents an operation whose duration is insignificant compared to the resolution of a state diagram. Action is an instantaneous operation within a specific time. It is associated to the event. An action represents the operation with specific time as compared to the resolution of a state diagram. A real world operation is not really instantaneous, of course, but modeling is an action indicates that we do not care about its internal structure for control purpose. But if we do care, then operation should be modeled as activity with starting event, ending event, and possibly some intermediate events. So action can also represent internal control operation such as setting attributes or generating other events. Such actions have no real world counterparts, but instead are mechanisms for structuring control within an implementation. Actions can also represent internal control operations, such as setting attributes or generating other events. Such actions have no real world counterparts, but instead are mechanisms for structuring control within an implementation. For example, an internal counterpart might be implemented every time a particular event occurs. In a computer, of course, even simple operations take some time, but they can be considered instantaneous with respect into granularity of real events under consideration. So the notations used for this action is a slash and the name or description of an action following by the event. So the pop-up figure shown here for the action. So this figure regarding you have studied the phone call state transition diagram for phone call. So initially this is state action for pop-up menu in case of the mouse buttons. So initially mouse is ideal state, then whenever we click the right button it will display whenever we click the right button it will display the menus. So menus are visible. We move the cursor or highlights menu, and suppose we want to go again in ideal state, then again we press the right button up or erase pop-up menu, so it will again go to the ideal state. This is in case of mouse button pressing. So summary of notation for unstructured state diagram. Suppose there are two states, state 1 and a state 2. So state 2 is depend on state 1 with some activity. If some activity done by state 1, it will goes to the state 2. So see this rounded, this figure indicates for state 1 indicated by this symbol, that is elliptical symbol denoted by the states, then state name, then there is some action do activity 1. So event 1 attributes, then some conditions regarding, then denoted by slash. Slash indicates the action, then the action 1, then it goes to the state second. This is notation for unstructured state diagram. So next part is nested state diagrams. So nested state diagrams, the state diagrams can be structured to permit conscious descriptions of complex systems. The ways of structuring state machines are similar ways of structuring objects, generalization and aggregation, which is studied in second chapter. The ways of structuring state machines are similar to the ways of structuring objects in generalization and aggregation. Generalization is equivalent to expanding nested activities. Generalization is equivalent to expanding nested activities. It allows an activity to be described at high level. It allows an activity to be described at high level, then expanded at lower level by adding details, similar to nested procedure call. In addition, generalization allows states and events to be arranged into generalization hierarchies with inheritance of common structure and behavior, similar to the inheritance of attributes and operations of classes. Aggregation allows a state to be broken into orthogonal components with limited interaction among them. Similar and object aggregation, hierarchy Aggregation is equivalent to concurrency of states. Concurrent states generally corresponding to object aggregations, possibly an entire system that have interacting parts. So nested state diagrams are classified into four parts. First, problem with flat state diagram. Second, nested state diagrams. Third, state generalization. Fourth, event generalization. So first, the problem with flat state diagram. So state diagrams have often criticized because they lack expensive power are impractical for large problems. Those problems are true of flat structured state diagrams. State diagrams. Consider an object with n independent Boolean attributes. Suppose there are n independent Boolean attributes. So here in this case we have taken n is equal to 5 that affect control, representing such structure with a single flat state diagram with 2 raised to n slides. So by partitioning the state into n independent state machines, however, only 2 n states are required. Here n is equal to 5, so 2n is equal to 10. 10 slates are required. So or consider the state diagram in which n square transitions are needed to connect every state to every other state. Minimum 2n, maximum n square. So in this case, the each object or each event is connected to other event or each state is connected to other event, so it requires minimum 10. See here there are 10 connections. This is first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, and 10th. So in this model can be reformulated using structure, the number of transitions could be reduced as low as n. All complex systems contain a large amount of redundancy that can be used to simplify state diagrams provided appropriate structuring mechanisms are available. So second is nested state diagrams. So in the previous slides we have studied the what is activity and what is the action. So an activity is a state can be expanded as a lower level state diagrams, each state representing one step of the activity. Nested activities are one short state diagrams with inputs and output transitions similar to subroutines. The state of nested state transitions forms lattice. That lattice is a tree structure. If it is a tree, if we it is a tree if we expand out different copies of same nested diagram. Lattice means structures. Then in this figure shows the vending machine structure. So top level model of vending machine. These diagram contain activity dispense item and are event select atoms that are expanded in more detail in nested state diagram. The diagram also shows a bit of alternate notation. See, this vendor machine is in initially ideal state. So this is a figure similar to the ATM machine. So whenever it is in ideal state, so a coin, then collect the money and add into the balance. So select item, it goes to the select item. So do test item and compute the change. If change is equal to 0, then defines the item, that is item is empty. Item is empty. Or if change is less than 0, then go to the collection for the money. But if change is greater than 0, then do make the change and go to the defense item and again go to the ideal state. So the lack of event level indicates that the transition fires automatically when the activity in state is complete. This is nested state diagram for the a vending machine. So this figure is one shot figure. So sub diagram of this figure is shown below this figure. So whenever you are inserting a coin, then the action is do move arm to correct row, then arm is ready, then do move arm to correct column, then arm is ready. If you have selected correct row, correct column, then push the element to that shelf, then element is pushed. So this figure is converted into one shot diagram as like this. Next, the event can be also expanded in subordinate state diagrams. This figure also expanded into this. Initially, it is in ideal state, that is reset atom. Whenever you enter some digit, so then goes to the state second, then append that digit to itself. If it is wrong, then it clear and go to the ideal state and stop. But if it is correct, then go to the enter and select the atom. So the customer key in an atom number and can start over by hitting clear. The selection is confirmed by hitting enter. The level on the bullseye indicate the event is generated at higher level state diagrams. Then third is a state generalization. The nested state diagram is actually a form of generalization on states. Generalization is the or relationship an object in a state in high level diagram must be exactly one state in nested diagram. It must be a first state or a second state or in one of the other state. An object in state diagram is a high level diagram that must be exactly one state in nested diagram. This is first step, second step or any other state. The state in the nested diagram are all refinements of state in the high level diagrams. So States may have substates. Any state may have substates that inherit the transition of their superstates, just as classes have subclasses that inherits attributes and operations from their superclasses. Any transition or action that can be applied to a state applies to all its substates unless overridden by an equivalent transition on the substate. For example, a phone line model would be simplified by replacing transition from one state to another state, that is from initially the phone or receiver at ideal state on the hook, with a single transition to super state to active ideal. All the original states except ideal are the substances of active. The occurrence of event on hook is an in any active substate causes transition to state ideal. So this is the figure for state transition diagram for the phone line. So initially neutral, that is in ideal state. Sometimes we sometimes we give a missed call, dial a specific number and stops. So that is push R in reverse and push N go to the neutral. Similarly, sometimes we call, then push F, then forward first step, second step, third step. In first step, sometimes we stop, otherwise upshift goes to the second step, then again upshift goes to the third step. Then whenever there is a downshift, then goes to the third to first, second, then second to first, then goes to the push n, then goes to the neutral. This is a transmission diagram for automatic transmission. This is state diagram for automatic transmission. Then fourth part is event generalization. Events can be organized into generalization hierarchy with inheritance of event attributes. Examples are events mouse button down, keyboard characters are two kinds of user inputs, that is mouse and user, that is keyboard. So both event inherit attribute time form. Event that event is a root of hierarchy and attribute device from the event user input. Mouse button down, mouse button up inherit the location from mouse button. Keyboard characteristics are divided into control characters, graphic characters. Ultimately, every actual event can be viewed as a leaf of generalization of the tree event. Inherited event attributes are as shown in second part of each box. So an input event triggers transition to any ancestor event type. For example, for example, a typing would be trigger a transition an event alphabet numeric as well as a keyboard character. Whenever a type letter A, we trigger transition as event alphanumeric as well as keyboard character. So this is a figure for event event generalization. This is figure for event generalization. So whenever event there is a specific time for that event, which is generalized into parts. Out of them, a single part is user input. User inputs, there are two types of devices. First is mouse, second is keyboard. So again, mouse button is divided into two parts: button down, button up. Similarly, keyboard is divided into two parts: control and graphics. These are two characteristics buttons. Then graphics is divided into again three parts: space, alphanumeric, and punctuation. Suppose I have pressed a button of keyboard, a letter A. Okay, so with that time, this is user input of keyboard character, then of graphic, then it may be alphanumeric. Okay, so then next part is a DFD, a data flow diagram. So data flow diagram is an OMT object, is an OMT diagram, that is the object modeling technology or technique that is added to the UML, Unified Modeling Language suite, whenever active the OMT model. What is the purpose of data flow diagram? So in OMT you can use DFTs to model what happens with data. You model the system as a network of processes that transform and exchange data. The DFDs shows the flow of data values from their sources in objects through the processes that transform them to their destination in other objects. Values can include input data values, output values, and internal data stores. In DFD, there are some inputs, there are some output, then there are some internal data stores, control information shown by in the form of control flow figures. So there are main four parts of DFDs: data flows. First is process, second data flows, third actors, and fourth data stores. And other parts are DFDs are constraints and control flows. So we will see one by one. First is processes. Processes are computational activities that transform data values. A process may be further divided into smaller components, and the lowest process may be simple function. Suppose I want to calculate HCF, highest common factor, and LCM, least count member. So we should know the two integers, that is this is input integer A, integer B, then this is intermediate process computing HCF, LCM, and this is the output, that is this is required LCM, this is required HCF. Then data flows. Data flows represent a data flow between two processes, from one process to another process. So it could be between an actor and process, or between data store and process. So data flow denotes the value of a data atom at some point of computation. This value is not changed by data flow. Suppose I want to calculate the sum of the digits from these. So data flow, this sum can be done of digits, this digit, this digit, this digit. Okay. Similarly, in case of name, every person have three types of name: first name, middle name, and last name. So this is a data flow from one part to another part. that is from data store to process or actor to process. Then what is actor? Actors are the active objects that interact with the system by either producing data or inputting them to the system or consuming data produced by the system. In other words, actors serves as sources and sinks of data. Suppose in a cloth market, the customer want to purchase a specific cloth, then he asks for to the sales processing, that is a customer details required, then it will check the sale by sales clerk details of that clothes, that is sales details, to the sale processing, and this information is said to the sales information to the customer. This is the acting. There are three types of actors shown by one. It may be act as customer, it may be acts as a sales manager, it may be acts as a sales clerk. It is denoted by only one actor. So, actors are the active object that interact with the system by either producing data and inputting them to the system or consuming the data produced by the system. In other words, actors serves as resources and sinks of the data. Then next concept is data stores. The data stores are passive objects. They act as a repository of data. Unlike actors, they cannot perform any operation. Data stores cannot perform any operation. They are used to store data and retrieve stored data. They represent a data structure, a disk file, or table in database. That is a storage. Data stores. Suppose I want to find a sales average, then there are records as sales record, average records. It is given by sales details. Then next part is constraints. Constraints specify the condition or a restriction that need to be specified over time. They allow adding new rules or modifying existing rule. So employee details, department and sale. This find incentive, okay, and another employee details department HR. So finds the increment. These are the constraint. Suppose there are another department as a storage, find the sales. How many storage? Then control flows. A process may be associated with certain boolean value. A process may be associated with a certain boolean value and is evaluated only if the value is true, though it is not a direct input to a process. These boolean values are called control flows. Suppose I want to do a division operation, so it requires divisor and dividend. Divisor test that divisor is not equal to 0. If it is true, then division operation can be done and we will get the quotient and a remainder. So control flows from divisor to a particular test and go to the divide operation. Similarly, dividend goes to the divide operation to perform specific division, and we will get the outputs as quotient and a reminder. This is the control flow from one part to another part. So this part is completed here. Okay.